Hi, my name is Ria, and this is Lab 4. So just to kind of jump right into things, the purpose of this lab was to model a real-world situation such as bungee jumping. And it's much simpler to use a mass that has a clear center of gravity than something that's a little bit more complex. So in this lab, we used a mass on a spring, whereas in the real world with bungee jumping, there would be a human, which has limbs and things, and that complicates the system a little bit. So a very simplified free body diagram. You can see in the corner right here, you have the force of the rope, or the spring force, pointing towards the point of attachment, which was in the positive y direction. And then we have the force of the earth, which is mass times gravity, that is pointing in the negative y direction. So the three main concepts that were tested during this lab were first Newton's second law, which is just that the net force is equal to the mass multiplied by the change in velocity over the change in time, the concept of a period, and then the law of conservation of energy. And in this case, there's no energy being added or taken away from the system, so delta E is 0. So I plugged the data from the video into Tracker, and you see I got this oscillation for both the x and the y data. And then going through the calculations that were shown in the videos, I was able to calculate the initial position as negative 206.44, the initial velocity as 0 as the mass is released from rest, and then working backwards was able to calculate the mass, the mass was told to be 0.402 kilograms. We know the gravitational constant is 9.8 meters per second squared, and then the period or the time per oscillation was 1.524 seconds, and then plugging that in, we were able to get 0.683 as the constant. Also, for the length of the spring, we were able to get 0.123 meters. So if you can see here, the glow screw code, I've broken this up into a couple different sections. The first section was to update the constant conditions. So we know, like I said, gravity is 9.8. We know the spring constant is 6.83. We know the relaxed length of the spring is 0.123 meters. And then we also know the system mass is 0.402 kilograms. And then we know the initial position of the ball, and that was captured by our tracker data. So here we updated the initial conditions of the actual data. We knew that the system energy, so the kinetic energy, the gravitational potential energy, the spring potential energy, and the total energy in the beginning would all be very easy to calculate just given our initial data. So the kinetic energy we knew was 1/2 mv squared. Gravitational potential energy is just mass times gravity times height, which in this case is the y direction of the position, or the y value of the position. We know the spring constant, which is just 1/2 times the spring constant multiplied by s squared. And then we knew the total energy was a sum of those three. So here, getting into the calculation loop, we knew while t was less than 10 seconds, which is how long it took the spring to oscillate. We have our initial energies, which we calculated outside the loop, and then we have our gravitational force, our spring force, and our net force, which is just the spring force multiplied by the gravitational force. The gravitational force is just the mass times the gravity in the negative y direction, and the spring force is the spring constant multiplied by the spring vector. And then we have the updating ball velocity, which is what we're using the loop to calculate, and that utilizes Newton's second law, which is just the initial velocity plus the change in velocity over delta t, and then we have that updating the position, which is just, again, a modification of Newton's second law, which it's the position of the ball plus the velocity of the ball over multiplied by delta t. So then, in order to calculate the energy changes, we use the same equations we've been using. So the kinetic energy is 1/2 mv squared. The delta K is the final kinetic energy, which was calculated in the loop, subtracted by the initial kinetic energy, which we calculated outside of the loop. And that was constantly updating, and a similar concept for the potential energy of the spring and the gravitational potential energy. And that allowed us to calculate delta E, as E was also constantly updating through the loop. So through the tracker data, I was able to get this cool comb-looking oscillation pattern. And then here we have the change in energy versus time. So the blue line here is the kinetic energy, and you can see that oscillating. The red is the gravitational potential energy, the green is the spring potential energy, and then the orange is the total energy. And as you can see, due to the law of conservation of energy, that's staying at 0. So what does that mean? For our model system, the energy law is satisfied, like I said, because delta E is 0, and we can see the period data has been regulated. So this also came from the Glos group code. This is just the position versus time of the actual graph. And as you can see, it's not the exact same. So this is just the model versus the predicted data, where the blue is the simulation and the red is the actual data that was taken from Tracker. And as you can see, there's some discrepancies, and I just think that's due to human error. Um, but overall, I think this lab was a great way to learn about the law of conservation of energy. Thank you.